Kira. Well, hold on, I gotta make sure that we're not. Okay. And okay, I think we should be set. Okay, I think everything should be set up. I'm going to make sure that live chat pop out. Got it. Okay. I think this will work. Be able to see questions in Discord and in the YouTube chat. Not sure if anybody's in here yet, but let me know if audio's okay, if it's too quiet or anything like that. Okay. That audio's a little quiet. All right. I'm going to bump the gain up a little bit. Hopefully that's better. All right, there's that. And my YouTube chat, pop that back up. Okay, cool. So this is the 2021 suspension design. We're going to go through how to create something that looks like this, and I'll try and walk you through pretty much all the major design decisions and where like you have to make decisions for yourself and based on what future cars are going to look like. But just as a quick overview, the way that I've set up this particular model starts out with the main constraints, which are the chassis and then both of the outboard wheels. And then we go through the actual process of creating the static suspension. And then we go through, in this case, I went through discrete analysis and like a bunch of really conceptual things. I might show some of these and how to create them, but a lot of these end up being unnecessary because I ended up going through and once I designed the bell cranks, I had a parametric solver where I just have wheel travel input, and from there everything is straightforward. I can monitor a bunch of different dimensions from there. So these discrete points, like we're still doing discrete analysis, but it's all parametric instead of having to set up individual sketches in various places. So yeah, so that's just a quick overview. Like I said, we'll go through everything, how to set it all up. And then just another preface, I'm going to be making a lot of use of my shortcut toolbar, which I've customized. to include a lot of stuff. So this is my features one. But if you want to customize these, you just right click on up here, anywhere in your tab, click customize, and go to shortcut bars. Or sorry, this is, yeah, I thought it was shortcut bars. Flyout toolbars, no. Oh yeah, here we go. Yeah. So you can change everything that's on these, within your sketch. This is the one that I've updated the most to include all the stuff that I use very frequently. So that's all in the customize section. Like I said, I'll be using that a lot just because I'm very used to not having to move my mouse up here and find the thing. It's right in front of me. Other than that, this is a pretty clean install of SolidWorks 2021, and I've just moved all my settings over from the last one, which is a pretty cool thing. And then, I'll have this existing model open as well. So we'll kind of flip-flop back and forth between the new model, which we're going to create now. So we'll create a part. Okay. And then before we even create any geometry, we're going to go through and set up all of the equations that we're going to need. For this, I actually have my old equations pulled up here. And the way I did them in the old file wasn't really, I guess it didn't really make too much sense. So we're just going to go through everything here. And I guess I'll just keep that down here. Okay. So first we're going to set up 6 variables that are pretty dependent on the overall vehicle is what I'll call them, kind of like just general setup. So one of these is going to be wheelbase. We'll do 1530 millimeters, which is just over 60 inches. It's basically just touch over what the rules minimum is. This can change based on your vehicle setup, of course. So, this is what we used for 2021. This is a change you can make. Then in my case, what I did was I set up the outer track of the wheels. What we went through was, in our case, a constraint was we wanted to fit our car inside of a U-Haul trailer. So we wanted it to be 60 inches from the outside edge of the tire to the outside edge of the other tire. So we started with the track in the front, and it was the outer track. And in this case, we had exactly 60 inches. And same thing for the rear. Cool. The other ones that are going to be pretty important are CG. And for this, you really want to do some kind of preliminary studies with packaging, create an extruded box in an assembly and set it as the weight of the accumulator, and then set other things as the weight of your motor, your driver, everything else, and figure out roughly where your CG is going to be. In our case, the height of the CG was 280 millimeters. And the other dimension that we're going to take is CGB. And if you look, actually, I should probably bring up paint. I'm going to need it a lot. So from a side view of the car, basics of CG measurements, we have the road here. Or I guess instead of that, I should just make a line that represents the wheelbase. And then we'll make a vertical line that represents our CG height. B is the dimension. I guess that should have been a vertical line. B is this dimension here. From the center line of the rear wheel to the line that's perpendicular to the ground where your CG is. So those are the 2 dimensions. You can pick A if you want. It really doesn't matter. It's arbitrary. A is this other dimension here. Oh, geez, that's way too far. But yeah, so that's A. This is B. We just picked B because a lot of this, in my case, when I set up the file, I started with the origin at the center point of the rear wheels, and then went forward from there. You can also start at the center point of the front. You can start at the CG, however you want to do it. But yeah, so this is the dimension we're talking about here. and that's going to be, what did we figure out? I think in our case, it looks like we were assuming a 50-50 weight distribution, or at least a little bit closer to the front. So we actually, in the design, specified for a 50-50 weight distribution, which one of the things within here that you can do if you wanted to design as close as possible to a 50-50 weight distribution, so you just say wheelbase divided by 2. But of course, you can also punch in. So in our case, it ended up being a little bit further, so we had 780 millimeters. And you always want to make sure to include your units if a variable has units. And then the last one that we have is the chassis ride height. And that's going to be 50 millimeters from the ground. Cool. So those are our 6 variables. Those are related to specifically overall car setup. And a lot of these don't really change that much. You kind of set them at the start of the year and then you keep them as they are. The only one that's really realistically going to change as you start to have a more fleshed out full car assembly model is your CG location. You can keep updating this. And then your chassis ride height, this should be a design input effectively. If you want your car to ride lower, if you feel comfortable with it, you can set that to be a lower value. But 50 millimeters tends to be a pretty good middle ground. From there, let me see here. What's the next part that we got to cover? Okay, so we have a couple of geometric constraints that we'll go into. It looks like we have 8 more variables in terms of geometric constraints that we're talking about. So one of these is a hub offset, and that'll make more sense once we actually go into the front and rear views. But we'll define 2. Actually, in this case, I had them as offset. I'll call them hub offset. Front, and this is 20 millimeters, and then hub offset rear, also 20 millimeters. Then we have 6 variables that tell us kind of the geometry of the tire, and then this is our tire radius in the front, and also you can make these variable names shorter if you'd like. I just try to make them as descriptive as possible. Generally, when we're actually defining these, we'll use the global variables drop down and we'll pick them as well, so you don't have to worry about saving character spaces. So yeah, our front tire radius is 9 inches in this case, and then one other variable that I defined was the tire loaded radius. And that was 8.7 inches. And this is a theoretical value. Basically, this would, accounting for the deformation of the tire as you set a car, as you set the weight of a 500-pound car on the ground, or 600 or 700 with a driver, that can affect some of the things with regards to your static ride height. So, looks like I had an extra quotation mark in there. There we go. Then we'll do the same thing for the rear. So tire radius in the rear, 9 inches, and tire radius loaded, 8.7 inches. Cool. And then the last 2 are, of course, our tire widths. In our case, we're using the same tire front and rear, but just for consistency's sake, front, so we'll have 7 inches, and this should be the width of the contact patch. Actually, if I remember right, that should be, I think that was 6 inches, if I remember. No, I think the tires are 7, but if the tire contact patch width is actually 6 inches, you can update that in here as well. You can also use overall width. Actually, I think that's right. So we're using, our tires have a 6-inch contact patch, but the overall width of the tire is 7 inches. And since we're working off of outer track, that's why we went with that decision. Width the rear, also 7 inches. Cool. From here, we're going to get into the stuff that's, well, I guess we can set some of this stuff up later. Yeah, let me look at some of this. Yeah, so I'll really quickly breeze through a lot of setting up a lot of the suspension geometry specific variables. If you don't 100% understand what some of these variables mean, like exactly what a kingpin angle is and that kind of stuff, don't worry about it too much. I'll explain it as we go along, and then also the Race Car Vehicle Dynamics textbook by Millikan and Millikan outlines them in a lot more detail. So I'll just breeze through. We got about, let me count 5. We got about 13 variables we got to fill in here real quick. So we'll do camber in the front. It's going to start at 1 degree static. This should be driven by tire data, of course. 1 degree as well in the rear. We'll have our kingpin angle. And we'll set that as 5 degrees. And caster front static 6 degrees. And you'll notice that a lot of these are static variables. We're designing, again, kind of for a static situation where we're at right height. This is what we want our geometry to look like. And then the philosophy is to analyze what that does afterwards, whether that's through just the built-in Solidworks parametric schedule setup, or if you wanted to export it out into a SimScape multi-body model, you could do that as well. So yeah, keep that in mind. These are all static values. As we start to cycle the suspension, they will change. We're going to define 2 variables called control arm ratio. And this is kind of something that I did, or hold on, control arm ratio. Hold on. There you go. This is something that I did for myself. You can either define both of the front, like for example, the length of the lower control arm and the upper control arm. You can define them separately, or you can define them based off of a ratio. The ratio of the lengths of the control arm is what affects your camber gain in cornering. So I like to set that up front, and then just kind of say, hey, my top one is going to be 90% of the length of my bottom control arm. And then in that case, you kind of have at least somewhat intuitive idea of what your camber gain is. Again, so a value closer to 1 will get you, or less camber gain. A significantly shorter upper control arm will give you more camber gain. Is kind of the relationship here. And then in the rear, we had a design ratio of 0.98, specifically because we had very long control arms. Yes, we had very long control arms in the rear. So we wanted to keep the ratio of the lengths much closer, and also the camber gain in the rear isn't as much of a factor as in the front. So let's see, roll center height is the next one. And of course, I gotta set this. I had this at 2 inches in the front and 3 inches in the rear. And these are kind of ballpark values of what is reasonable. You can fiddle around with these a little bit. Generally, you want to keep your front roll center height lower than your rear. So the roll axis going between those 2 lines, which we'll actually illustrate once we start creating all the geometry, it pitches forward. All right, so last 5 variables. Scrub radius in the front is going to be 1 inch. And this is a little bit different, I guess. Not everybody uses scrub radius as a driving dimension. Oftentimes it's measured after the fact. I found that it was much more helpful for me to just set a scrub radius and then build the packaging of the outboard suspension based off of that, rather than trying to kind of figure out lengths of various points by the wheel. and using that as driving dimensions. So setting a scrub radius at 1 inch for our car is fairly reasonable. Then we have two variables that define camber change rate. And here per inch of travel. And then same thing in the rear. And so this, coupled with our control arm ratio, both of those will end up influencing, the exact lengths of our control arms. And then we have our front view. Actually, I think I'm going to define both these as we start going through the sketches. So this is kind of what you'll start out with. Again, these are kind of, I guess this summarizes what all of our driving, these are our driving dimensions basically. This is what the entire suspension is built off of, is deciding what are reasonable values for all of these. And I guess for your tires, that's not really so much about reason as it is about what tires you have, but generally speaking, you try to figure out what a good wheelbase is, what a good track width is, figure out where your CG is going to be, and try to design that and mold the design of that towards kind of what your design specification is. And then you start to figure out a few things about, well, okay, what's the ratio my control arm is going to be, of the length of them, and then also where's my roll center going to be, and a lot of stuff, as you'll see as we start diving into this, is dependent on outboard packaging. So we will save all of those equations in there, and of course good practice is to save your stuff as you go. So right after that, we'll go ahead and drop it in there. I'll just label that as demo. And like I kind of mentioned before, if you guys have any questions, drop them in Discord or in the YouTube chat. I will try and answer them as we go. Cool. So we save that in our Kinematics folder. And so our first step now is to start creating our reference sketches. So we're going to, actually one of the things that I did was I renamed, this is something that I didn't do in the initial one. So one thing we're going to do real quick, if you hit your space bar, that brings up this orientation fly bar. You can change which axis is pointing up. And if you remember, or if you've read a little bit of RCVD, you'll start to notice that they're using Z-axis as up, and X-axis is forwards, and Y is kind of the turning axis. So we'll switch this to Z up. So now you can see our Z-axis is pointing up here. And then we'll start to rename. We'll rename our plane. So in this case, our front plane is actually just XY. So this is going to be our ground plane. Our top view is our side view. And then what was the right plane is now going to be the rear axis center, or rear wheel center line. Or I guess axle is probably better. There we go. Cool. So rear axle center line, that's that plane. Then we have our side view plane, and then we have our ground plane as well. And that's what we're going to build everything off of. In my case, when I started off this suspension model, what I used was the chassis side view as my first sketch. This is something that you'll have to talk to whoever's designing the frame. This is where you'll start to build things up. And so let's actually go ahead and make that sketch. And that's fun. Hold on. Okay, so there's our front view. For some reason, decided that our z-axis is going to be pointing in a different direction now. Neat. So we'll just spin that around. Alt and arrow keys will spin stuff around for you so you can see the z-axis is pointing up now. And we can go from here. Cool. So we'll start by creating, again, this is, remember, our origin's located at the rear wheel center line. So we'll make a horizontal line going towards the front of the car. You can see X is pointing forward. So we'll make this is going to be our wheelbase. So we can just make this equal to the wheelbase. You can see as I start typing it up, it's going to pop up. I can click on it, brings that in. I can hit OK. And for some reason, we're in meters here too. So use Solidworks 2021. Haven't adjusted my settings yet. Hold on. Document properties, dimensions. Maybe I should just switch to ANSI drafting standard. Okay, there we go. That fixed it. It was showing me in meters. I just want millimeters. So 1530. Remember, that was our wheelbase there. One thing that I did was I created a solid line just to represent our CG. We'll do the same thing. Go in here, equals CG height. There we go. And then distance from here to our origin point. Or one of the other things that you can do is if I show that plane, I can actually dimension from here to the plane itself. If I can click the plane. There we go. And that can be sometimes a more reliable way of going through and actually setting up your dimensions. If you end up changing your reference planes or something like that, at least you know which plane you're always dimensioning off of, and it's not based on some origin that's defined for each sketch. So there's our CG location, and then a couple of lines that I drew. I drew in our main roll hoop location. And then for our 2021 car, we had a rear bulkhead that drove some of the dimensioning. We had, again, in our case, we were going to the front roll hoop, and then we also had another line up here. And basically what we're setting up here is kind of from a side view. We're looking at just the chassis and where we're going to be mounting our suspension points to. You don't have to set this up initially, and especially if you don't have it, you don't have to go through this 100%. Actually, yeah, Gary, that's a good point. The wheelbase should be 50 millimeters above the ground plane. Thanks for catching that. So let's do from that to ground plane show. Cool. Equals, and this is our chassis ride height. And then it should still be good. Constant. Cool, good catch. Let's see, what else are we missing here? Yeah, then you'll have to go to the chassis model and gather whatever dimensions you need from that. Kind of see some of them here that are main roll hoop. Let's see, how did I dimension these in this case? I started, yeah, from the rear bulkhead. I think I had yeah, so I set up a couple of lines here. Let's go pop over here. And then we're also going to make another separate construction line here. These don't have to have a specific height or anything like that. It's mostly just their front to back location that matters. Yes, Gary, you're correct. And then this CG location is mostly just for representation's sake. I didn't end up using this actual point in my calculations or in any of the future sketch setup, but yes, we'll do CG height from the ground plane too. Cool. And then yeah, so here we had, I think I had like 150 millimeters going towards the rear, 150 forwards, and then between, I think it was between this rear axle center line and the main roll hoop was like 800 millimeters. And these are all, like this line is mostly just for future assembly mating too. One of the nice things about this is I can just set up, again, if we have a ground plane that's shared within the main assembly, we can just mate ground planes together, or we can mate, center lines of roll hoops or other stuff like that. So that's stuff that we can do. In this case, what I'm actually going to do is I'm going to set something up a little bit differently. So instead of mounting to the main roll or to the front roll hoop, I'm going to make this a vertical line, and then we'll just say that we'll mount, we'll just have 2 suspension nodes at 150 millimeters plus minus from the front wheel as well. But yeah, like I said, in this case, all we're doing is we're trying to create these 4 lines here that are going to be the inboard mounting points longitudinally. We're not really caring so much about width or height or anything like that. These are just kind of where it makes sense to plop down some vertical chassis members or any of that kind of stuff. In the rear, if we have a bulkhead, or if we're going off of the rear, the rear of the chassis, or where the diff plates are going to be, all that kind of stuff. This is all reference geometry for now. And then I think that should be it. Let me just double check to make sure I'm not forgetting anything from our chassis side view. Yes, that should be, yep, that should pretty much be everything here. So yeah, we had, this was our front roll hoop that we were trying to mount to before. And I think I ended up changing some things anyways. But yeah, so we set up our chassis constraints first. That's kind of good practice to figure out what am I dependent on from other subsystems. Cool. And so now we have something that looks like this. From here, we're going to click and control click and drag to create an offset reference plane from the rear axle center line. And this we'll actually set this as just some arbitrary value for now. This is going to end up being our front axle center line. And then if we click on this plane, it's going to bring up the dimension that made that. So we can set this to be equal to our wheelbase. One of the other things we could do here is we could just make it coincident. Yes. Yeah, so we can make it coincident to our wheelbase. Did I delete? Hold on, let me double check something here real quick. Nope, that should be correct. Just looks kind of funny. Okay. There we go. Okay, so we have our front axle center line, we have our rear axle center line. From here, what we're going to do is we're going to start setting up the front and rear outboard constraints, and we're going to start building the suspension from the outside in. So we'll start, let's go with the front tires first, and of course the axes are all messed up as well. Actually, one thing that I could do, I think if I do this, get the standard views front. Okay. Let's see if that helps. It's probably not. Nope. All right. I guess we'll be doing this for a while. Cool. So from here, basically what we're going to do is we're going to create a representation of a tire to start. And we're just making this some arbitrary shape, and we're intentionally cambering it as well. From here, we're going to make sure that the midpoint is lying on the ground plane. And then we'll start setting some dimensions. Actually, we'll also set both of these to be the equal length. And we're going to dimension this top one. And also be careful of this dimensioning as well. This is partly why, again, the static camber here in this case is going to be 1 degree. This is a lot more than 1 degree. One of the reasons why I'm doing this is just so that I can make sure that I'm not dimensioning the horizontal dimension. I'm actually dimensioning the length of that line. We're going to set that equal to, this is the front tire width. Equals front tire width. There we go. And then we'll have the tire radius in the front, and then we'll also do the loaded radius in the front too. Cool. And just like that, we have a tire, or effectively what a tire would be. I'm going to bring up the other sketch just to make sure. In this case, we did front first. I guess this is effectively what we're trying to make here. So we're going to create a couple of extra center lines. We're going to define our overall track width. And this was our internal wheel shell deck, which I guess could also be a global variable as well. So we're going to make some center lines real quick. So from there to the midpoint. And then you want to make sure that you don't snap to the midpoint, because again, this bottom section is shorter than the top because the bottom section of the tire is loaded, the top section is not. So we'll just manually add a perpendicular constraint there. And then we will add in, we'll actually make a midpoint line from here. And then we'll start defining something that looks like a wheel. And I guess I should connect these two as well. All right. So these two are going to be perpendicular to each other. Same thing with these. And for some reason that made a midpoint line, so we'll trim that away real quick. Hello, delete. Okay. All right. And again, just adding a couple of constraints. You really want to make sure to add as many constraints as possible. Well, not as many constraints as possible. You want to start with defining your constraints and then add in dimensions later on. And then, yeah, in this case, I think we had, I think it was like a 9-inch internal wheel shell. And then here's where that hub offset comes in that we defined earlier on. Offset front. Just double check. Yep, so this is the hub offset. This is basically how far outboard from the center line of the wheel the hub is going to be. Or I guess this would be more of like a wheel shell backing or whatever else. Basically how far out we can go in terms of actually defining, placing points and whatnot. We don't want to be past this line here. So I call that hub offset. You can probably find a better name for that as well. But yeah, so other than that, we have only a couple of things left to define. And that's going to be, back to a normal view, and rotate this thing around. One of the things I'm going to do is I'm going to create a center line here just so I can do one of these dimensions here, which is to set the overall track from the outer points. And I just used the center line there, dragged it to the other side of the center line, which gives what it calls like a diameter dimension effectively. But essentially it's dimensioning between this point and a theoretical point that's perfectly mirrored around this line. Then one of the other things we'll do is we'll dimension between the ground plane and the bottom of the tire, and that'll set our static caster, camber. Static camber front. Cool. And from here we're pretty much set. This is all that we need. Again, just double checking. We have our unloaded, our loaded tire radius, our hub offset, tire width, inside wheel shell diameter, our static camber angle, and then our overall track width. And this is all we need to set up one tire. We'll do the exact same thing on the rear, and hopefully that'll go a little bit smoother. Okay, again, that's on our front plane. We can hide some of this stuff too if we wanted to. And also renaming as you go is a good idea, something that I'm pretty bad at. Chassis side view. And this is front wheel assembly constraints. Do the same thing for the rear now. I'll hide that just so it's easier to see. Oh. Bring that back. Thing here. In this case, I'll go around and create the entire wheel shape first, and then I'll add constraints to my center lines, and that should hopefully help a little bit. Make those two equal length. A split. This is one of the other tools that is kind of hidden within Solidworks, is the split entities. Basically, I can just plop down a point, and now instead of that being one line, it's actually two separate lines. So that's a very helpful tool that, like I said, is kind of hidden within Solidworks, but you can customize this to have that be readily accessible. Cool. Perpendicular. And I'm going to select the midpoint of this line through the right-click menu and make that coincident to that. Cool. So if I temporarily fix that point, I can rotate this back out, hopefully. What do we have? That's what the problem is. Cool. Okay. That's one of the neat uses of the fix command as well. If you ever find something that's, like in that case, I saw that, hey, everything snapped vertical. I want to make sure that I can still rotate this around. I fixed the point, and then it showed me that these construction lines were vertical and horizontal. So I can delete that relation really quick and make sure that everything can rotate the way that I wanted it to. So again, same thing, tire radius here. This is our loaded rear tire radius. And up here, oh, drag it too far out. Radius loaded, tire radius rear. One of the other things to watch out for, so you can see in this case, I have that little sigma right next to the variable, and then in this case I don't. In this case I forgot to type in equals before I did tire radius loaded rear. So that's one of the things with global variables. You can either use them to drive stuff, or you can just use them to set like a reference value. So yeah, in this case, we want to make sure that everything's still driven from our equations. So that sigma shows that the equation is driving the value of that variable. Cool. So then we have our hub offset here. And this can be different in the front and the rear as well, based on how you set up or how you have your wheel shells. If you have wider tires in the rear or wider wheels, different back spacing, different upright geometry. There's a lot of different reasons why that could be differently sized. So I tried to make this as, like in this case, again, we have hub offset front and rear. When we know those are going to be the same value because we're running the same wheels and same uprights front and rear. But again, this could change. So let's see, we're doing tire width in the rear. Yes. And then all we need to do is plop down a center line here and dimension between here. And you can see here it's basically a radius dimension. Here it's a diameter. So dragging that over gives us track rear outer. And last but not least, we got our camber equals static camber rear. Oh, and then of course we got to figure out, grabbing that midpoint, make sure it's coincident to the ground plane, and set our 9-inch internal diameter. There we go. We have a fully defined sketch. Exit out of that. And this is rear wheel assembly constraints. Cool. So these 4 we can group together in a folder. These are our constraints. And again, these are things that probably won't really change. You generally decide on what wheels and tires you're running before you start designing a suspension geometry around them. And so yeah, we have both of those finished. And let me just again pop back over here. You can exit out the sketch. And then I'm not sure if all of you are familiar, but what I just used there was the D key. So when you have those buttons up here at the top right section, the exit sketch and the close, you can use D to bring that right to your fingertip, kind of like the S key fly out. So this next bit is going to be the tough one. And this is where we really start to delve into some of the fun things about suspension geometry design. And this is what our front suspension front view looks like. So what we'll do is we'll go ahead and pop back over here, start a sketch on this plane, and get right to work. The other thing we'll do is we'll make sure that the front wheel assembly is visible. I'm going to hide some of these planes. We know where we can get to them. Ground plane as well. So we'll hide that. Cool. So we have our center line of our wheel right here. We're going to start by creating a line that goes from there. And I'm going to make sure that I drag this far enough out that I know that it has, in this case it says vertical because our orientations are a little messed up. But it's a straight line. It's not snapping any relations to the rest of this existing sketch geometry. This is going to be our scrub radius line. Of course, it's going to be a lot shorter than that. And then we'll have our kingpin inclination going up from there. I'll also create a vertical reference line going up. And then, let me just double check to make sure. So yeah, we had those two. I don't know if I show the front wheel and tire. Yeah, so this is what we're going to be building off of here. And this will all make sense shortly. Cool. So again, I should make sure these two are perpendicular. Okay. Right, so remember, this is our scrub radius that we defined before. Scrub radius front. Okay. And then this line right here, the angled line, is actually our kingpin axis. So we're going to define our static kingpin angle right there. And then along this line is where we're placing our outboard suspension points from from the front view. That's where they're going to end up. If you look from the front, you'll see that there's going to be a suspension point. There's going to be a control arm going this way, and then there's going to be a control arm going that way. And yeah, we'll also create, we'll go ahead and, actually I'm going to do this a slightly different way just to make sure that I got all of my constraints in order. So what I'm going to do is I'm going to create these two lines that intersect, and these are going to represent our control arms. And then I'm going to go back to that point where the center of the tire contacts the road, and then I'm going to make sure that that's coincident there as well. Then going back to that split entities tool, I'm going to split this, split those into two separate items, and then those three will become construction geometry there. So that's a really easy way. Now if you look at this, it already has that collinear constraint there. Same with this one. They're all coincident at that point. This is pretty much, we're starting to set up our roll, our instant center, which is this point out here, and then shortly we'll set up our roll center, which will go from here, not to the midpoint of that line, but just to that line. Cool. And then one of the other things, I don't know if you guys noticed this about Solidworks, but it starts to highlight the horizontal or vertical constraint that it's closest to. So that's another nice thing if you, like we are in this case where we have to rotate our views around, it's really easy to pick out which one is the correct constraint. So we'll make sure that that's horizontal, and we can define this line as our front roll center height front. There we go. Cool. So now we have this line defined, and one of the things you'll start to think about, if you have read through parts of RCVD, you'll hopefully be familiar with the term front view swing arm length. And that's basically the length of this arm, if it were just to be fixed around this pivot point. And that's one of the things that we're going to use to drive, to actually drive our design here, is this value here. So we haven't defined it yet, but we're about to. And this is front view swing arm length front, short abbreviation there. But yeah, basically what this does, a longer front view swing arm is going to make it so that your camber change rate is, or I guess stays more consistent. So the derivative of your camber change rate, kind of is smaller. Hopefully that makes sense. So I guess I'll make this really short here. Oh no, I don't need a control tab. There we go. So if I make this really short, you can see both my control arms are pointing up. They're already starting that motion. And then as the wheel moves, I guess it's kind of hard to show within this sketch here. I guess, I don't really have a particularly good way of explaining it. But generally you want to have a fairly reasonable length of a front view swing arm, and it ties into your camber change rate. So we'll go back into our equations real quick. And one of the nice things about equations is you can start to create variables, kind of like I hinted at this earlier, but you can make variables depend on each other variables, and you can do math, you can do Boolean logic, you can do all sorts of stuff. But we'll start defining those. FVSA, length front, and then in this case, this equation is pulled straight out of race car vehicle dynamics, or solved for out of race car vehicle dynamics, but we need our camber change rate, that, and then multiplied by 1 inch. Cool. So that'll calculate out, it'll do all the math for you, and then we'll do the same thing for the rear. 1 over the tangent of camber. Just pull that there. Cool. And then the 1 inch here, that just comes back from this. Since you can't really define like degrees per inch as a unit or anything like that, we make a note here that it's per inch of travel, and then we just account for it within this calculation here. So actually I have RCVD open here. I'm going to really quickly see if I can find that equation. Should be pretty quick to find, hopefully. Yeah, so it's on page 615 within figure 17.9. Camber change rate equals inverse tangent of 1 over the front view swing arm length. So kind of back solving for the front view swing arm length, we can establish that just by going about kind of setting a desired camber change rate for both our front and our rear, and then we can define what the front view swing arm length is going to be. And that dimension, let's go back into the sketch. That dimension is measured from the wheel center line to the instant center along the lateral axis. So you want to make sure that this isn't the length of this theoretical line, it's actually this horizontal distance. And so this is our front view swing arm length in front. Cool. Hopefully that made sense. I'm going to pop back over to my chat just so I can see everything. Yeah, cool. So from here, we only have, kind of remember we had our 2 dimensions here, or a ratio that's going to come into play here shortly. We'll use some driven dimensions to accomplish that. Basically, what we need to decide is how wide can we really spare to have these suspension arms. And this is, again, a chassis constraint. Wherever your driver's legs are going to be passing through the middle, this is mostly what's going to drive that. In our case, for the 2021 car, we were planning to mount the lower control arms outside of the driver envelope, so we didn't have that as our driving factor. We actually were driving more of the upper control arm length. So we'll go back to this sketch here, and we'll assume that it's the same case, that we're driving, and we already have a vertical center line here. So we'll assume that we can only have no less than 600 millimeters between left and right suspension points. Again, this is going to be driven mostly by driver constraints, where you can pass your legs through. If you're going to narrow this or widen it, this is what it'll adjust. But generally speaking, from what I found at least, you want to have these control arms be as long as reasonably possible. So that kind of helps out more with transient behavior. Again, we're setting up the suspension more for static or based on static constraints at ride height. And we want this behavior to be, or we want the suspension behavior to be close to this as we start moving through bump and droop. So having longer control arms means that there's less change in your instant center location and your roll center location, which again we'll demonstrate later. And then we'll make this a driven dimension. Oh, actually, that's the other thing that we have to set before we do that. Hold on. So based on your upright geometry, this is where these 2 dimensions will come into play. So we'll have something like 85 millimeters here and 95 here. I think that's what we had in our last car. But basically, this is the distance from the center point of your center line of your wheel to the lower ball joint location and to your upper ball joint location, respectively. Again, this is upright dependent. So if the suspension designer is doing stuff, or the kinematics designer is doing things independently from the upright designer, you want to make sure you communicate. RCVD goes into this a little bit, but generally speaking, having these closer together, having these further apart is more desirable. It results in a stronger upright assembly. It also means that if your hole is slightly out of tolerance, it's going to affect the suspension less than if these 2 points were very, very close together. It would kind of have less of an effect on your kingpin angle and the rest of your outboard wheel assembly. So that's something to keep in mind. You generally want to space these out and kind of fill out the wheel shell as much as possible. Keep in mind, though, you will have to watch out for running into the outer edge of the wheel. or your wheel shell. So these are the two dimensions you'll want to adjust for that. And again, do that in tandem with whoever's designing the suspension uprights. Cool. So we'll make a driven dimension here, and then we will drive this lower control arm based on this divided by our front control arm ratio. Yeah, control arm ratio front. There we go. So again, remember when we defined that was the ratio between the upper and lower control arms. In this case, our upper control arm is the shorter one, and that's the one that we're driving with our constraints. So we're going to divide by that ratio instead of multiplying. So yeah, we have a longer, lower control arm now. And again, everything is fully defined. So our work here is done. Cool. And then kind of like I mentioned, D key before, if you're working on something here, you want to get out of your sketch, press D. It brings the exit sketch button right to your fingertips. Cool. So this is front view. Guess what did I call it over here? Front view. Front suspension front view. Got it. Cool. And we'll do the exact same thing in the rear. And again, this should be pretty much straightforward, just what we did before. So good time to ask questions if anything was unclear in that last little bit there. So we'll hide that. We'll hide our wheel. We'll bring up our rear wheel. And then we'll go to our rear axis center line to make a sketch. And Alt and rotate. And then in this case, our scrub radius doesn't really affect things. This is kind of a point where you can make a little bit of a decision where you can say, hey, am I going to have front and rear uprights be identical, offsets be identical, all that kind of stuff. And then that's where you kind of start to place, this theoretical axis where your points are going to be located on. So in this case, yeah, we are using the same design of upright front and rear. We're making that coincident there. This is still going to be our front scrub radius. We don't technically have a scrub radius in the rear because we're not steering the rear wheels in this case, which again, that could also be a design decision that teams may want to go on later on. Okay, and again, we'll make sure, this is something you always want to keep in mind, is make sure that when you're drawing stuff here that you know what you're referencing, basically. Cool. And then we'll do same thing, kingpin angle. Everything is the same as the front. So equals kingpin front static. And we'll do the same thing. We'll draw a line going out here, another line here. Double clicking within the line tool also helps. Like in this case, it wants me to draw another line. If I double click, it stops drawing that line, but it keeps me within the line tool, so I don't have to hit escape, pull up the S key, and get back into the line tool. Go split, and we're going to mark things as construction geometry. Then we will draw a line from origin to that. Make this horizontal or vertical. We'll set this to our roll center height in the rear. We can also go ahead and set our front view swing arm length. Decide that, yep, we're going to have 95 millimeters going down and 85 going up. Not just 5, 85. Cool. And then in this case, again, we'll, or I guess just to give another example, in our case, we had our differential being the main driving factor in the rear because we had a couple of plates going out the rear of the chassis. Those are what picked up the differential, and then that's what we mounted our suspension off of. So this is where we set the minimum distance between 2 points, and because our lower control arm is going to be longer than our upper one, we're going to drive that one instead. That's going to be, again, kind of that's what's constraining us. So we'll just set something arbitrary like 335. I think that seems about right to what we were doing. We'll create a driven dimension here. And again, in this case, with how shallow that angle is, you want to be careful. And this shows 469.25. And then if I drag this over so that it's the actual length of that line is 469.43. So it's 0.2 millimeters, but you want to make sure that you're dimensioning the thing that you want to be dimensioning. And then same thing here. This difference there. In this case, this is going to be this multiplied by our control arm ratio in the rear. And actually, because of that kingpin angle and how steep we had this set, I might actually adjust this to 0.95 and say OK. The automatic rebuild checkbox down here is also pretty helpful. But basically what I saw there was that our upper control arm was going to be poking in further than this lower control arm. You could change that by just making this drive that point instead. One of the other things you could do is you can say, hey, I don't really care too much about the ratio between these two lengths. I actually just want these 2 points to be right on top of each other, because that way it makes it a lot easier to mount to my two vertical plates that are going out back. I don't have to make a bunch of different tabs. They can all be pretty similar. So instead of that, we can also do something like this, where we just forego that dimension entirely and we just make those two coincident. So you can see now these 2 points are right above each other. And again, there's pros and cons to all of this. And honestly, I don't think too much of it really matters all that much, at least in a formula environment. So just keep kind of your design decisions in mind. You can either drive this based on ratios, you can drive it based on packaging. As long as you can justify what you're doing to the judges, that's ultimately the most important thing. So cool. So now we have our rear suspension front view designed. And we'll just take a quick peek at this one here, because I think that's what we ended up doing in the rear suspension. Yep, that's exactly what we ended up doing. And actually here we had only 200 millimeters between the two control arm pickup points. So we had the vertical line here, made it so that the tabs were a lot easier to manufacture and to make everything mount up properly. And then again, we had that 5 degrees. And then we had, actually in this case, we had a different dimension driving. I think I ended up measuring off of the other sketch here. But either way, like I said, if you're running the same upright front and rear, just use the front dimensions to drive the rear dimensions as well. And that way your outboard packaging is going to be on point. Cool. So now, one of the fun things we get to do is create side view geometry. And this is one of the most kind of mind-boggling things about suspension. I still don't 100% get it, but it kind of sort of makes sense sometimes. One of the things that I built into this into the suspension solver last time was separate constraints for front and rear wheels and their side view instant centers. And if you want to read about side view instant centers, that is all outlined starting on page 617 in our CVD. And we'll have a couple more equations that we'll use to drive all of that stuff too. But basically what I'm going to do here really quickly is, just for ease of illustration, actually let me hide this. For ease of illustration, I'm going to go in and I'm going to change the rear outer track to 80 inches. And the reason I'm going to do that is just so that I can keep track of where I'm working with the front suspension and where I'm working with the rear. And this is also a good point, good point to stop and check and make sure that, hey, okay, all my dimensions look good, they all look correct. If I rebuild, rear suspension, front view, yep, that looks good. Yep, that all looks good. Make sure that you didn't miss a driven dimension somewhere. An equation-driven dimension somewhere. You can also hide the chassis side view. Cool. So what we're going to do now is we're going to bring up both of our wheels. Actually, we'll bring up both the front and rear wheel assemblies. And we will make reference planes off of the side plane. So again, control, click, drag. And we'll make one for the front. We'll just pick that center point of the wheel. And that'll be one plane. Let me do this real quick again. Pull up my chat so I can see if you guys have questions. Cool. So we'll do that. And then same thing, side plane. Again, pull that out so it's parallel. And then make it coincident to the rear wheel. So again, if our tracks are identical front and rear, these two planes would sit right on top of each other and it'd be kind of hard to tell what's what. So in this case, I just made the rear one further out, and then I'm going to change it at the end, and hopefully everything will rebuild, and then I'll know I'll have a good solid model too. Cool. So this is our front suspension side view plane, or I guess this would be front wheel, and this would be rear wheel. Also good practice, if you're naming a plane, add plane to the end of it, because then if you want to make a sketch that's called the rear wheel side view, it's not going to let you kind of do that, or then a feature that's rear wheel side view. Kind of adding extra unique bits here and there can be helpful if you start building up a lot of stuff that's renamed. So yeah, we got that there. I'm going to grab some water real quick. All right. So now the fun part. And that's going to be front suspension and rear suspension side view instant centers. And this is what the sketch looks like. We have a... pull this guy up. Oh yeah, so we set an arbitrary length of a line here. In this case, I just did 3 times the tire just to have something long enough and fully defined. And then we have these 2 angles here. So there's that one. Actually, we have in this case we have 1 angle that defines one thing. We set an arbitrary value for the front, and I'll explain why here in a second. And then we have our 6-degree caster that we also define from the side view. So I guess we can talk about let's kind of go conceptual. So from the side view, the main things that are controlled are your anti-dive, anti-squat, and anti-lift properties. Those are all outlined again in RCVD. It kind of explains a few things about them, and it's kind of hard to tell what a reasonable value for a lot of those things is. And again, that all kind of starts 617 or page 617 onwards, section 17.3. So it kind of goes through, talks about all these calculations for calculating anti-dive. Couple things to keep in mind. Let's see if I can pull up my old notes here. Yeah, so anti-lift in the front only applies to front wheel drive cars. So that's kind of why, if we go back to this sketch here, I guess the rear wheel would be a better sketch to show. Yeah. So in this case, we have 2 angles. These are driven by our anti-squat and anti-dive, anti-squat and anti-lift. And basically what that is, short way of explaining it is, anti-squat, it's the amount of force that is absorbed by the control arm itself rather than the spring under squat loads. That's accelerating the weight transfer to the rear. How much of that is actually going into the spring damper system versus how much is the control arm actually taking, or both of the control arms, front and upper and lower. And then with lift, it's the same thing, but under braking, weight transfer to the front. How much of that load is, kind of how much of that weight transfer goes into the shock absorbers versus how much of that is load removed from the control arms. Hopefully that makes sense. From my discussion with industry experts, it seems that, kind of values between 10 and 15 or maybe 20% is what's reasonable. Initially, when I was designing this, I was using values of like 80 or 85%, which I don't know. It's not really intuitive for me, but which is why I consulted industry experts. You can run some studies and go through and look at all that and kind of figure out kind of what makes sense at the end of the day. But basically, the three values we're going to define now, going back to our equations in this one, this file here, we're going to define anti-squat in the rear. And we're going to define that as 0.2 is what I had. Let's do 0.15. So about 15% anti-squat. Potential circular reference. No, I don't have a potential circular reference. We'll do anti-squat. We're going to do anti-lift in the rear. We're going to do that as 10%. I had an extra quotation mark there. And then we'll do anti-lift in the front. That's the anti-lift in the front, kind of same thing I was talking about before. Under acceleration, weight transfer, how much are those front tires going to lift up, and how much is the geometry of the control arms going to prevent that? So here in this case, we're saying 10% of that load, the control arm is going to prevent it. 90% of it is going to go towards upsetting the suspension. Cool. And then from here, we're going to calculate those angles. In RCVD, it describes both of them. Or actually, no, it doesn't. It describes let me look at this again. I'm trying to remember how much of this I came up with and how much of this I just pulled from RCVD. Okay, yeah, so anti-lift, or I'm just trying to remind myself of everything that I did 9 months ago. Okay, so anti-dive, basically in that section it goes through some of these forces are evaluated at the ground, and some of these forces are evaluated at the wheel center line. And based on pairing those two up, we can just have two angles, one of them evaluated at the front wheel center line or center point where it contacts the ground, and also from its center line where those two lines intersect. That's our side view instant center. We'll kind of build that up here. But first we have to calculate those angles. To do that, we use those equations that are in RCVD. We back solve for the actual angles themselves, because in their case, what they actually do is they take an existing suspension and they try and calculate what the anti-dive is. In our case, we want the anti-dive to be an input into it, so we back solve. Cool. So we'll define phi in the front, and phi is the angle between the ground contact point, or the ground and the line going to the instant center from the contact point with the ground. Phi is going to be the arc tangent of anti-dive in the front. One second, hold on. Oh, that's right. Anti-lift front. This is the one that's only for front-wheel drive cars. This needs to be anti-dive. There we go. So yeah, technically you can have an anti-lift in the front too, but that will only matter if you have a front-wheel drive car. Rear-wheel drive is concerned with anti-squat in the rear. Cool. So phi front is going to be arctangent of anti-dive front divided by, oh, that's another couple things that we forgot to define here. Hold up. So kind of backtracking a little bit, remember, dive in the front, lift in the rear, both of those are with regards to braking action. So we actually have to define how much of our brake proportioning we're putting towards the front and towards the rear. And this is kind of hard to define exactly, but generally speaking, what I've been going with based on my reading is that front brakes is generally about 75%, and then rear brakes is 25%. Or if we wanted to make this a little bit more robust, we could just do 1 minus front brakes. And make sure that's a quotation, not an apostrophe. There we go. All right, so let's actually define phi. Arctangent of anti-dive front divided by front brakes multiplied by the CG height divided by the wheelbase. Cool. And there is our angle. And then same thing here. We're going to do phi in the rear. And in this case, it's the anti-lift in the rear that's driving it, divided by rear brakes, multiplied by the CG height, divided by the wheelbase. Do we need to close the parenthesis? Yes, okay. Then theta is the other angle that we're defining, and we're only defining this in the rear because this is what's dependent on anti-squat. And then in the front, we'll just set an arbitrary length of how long we want our side view swing arm to be. So we'll do anti-squat rear multiplied by the CG height and divided by the wheelbase. No, we need to do arctangent of this stuff. Cool. And then one other quick thing to double check, or one little sanity check, you want to make sure that phi is greater than theta. So in this case, that passes that check. And that shouldn't need to see the equation screen anymore from there. So just hit OK. All right, so now we get to, I'm just going to hide that, draw a sketch on the front, the side view plane for the front wheel. We'll define a line, set that, again, that's just some arbitrary length. Before I use 3 times the wheel radius, it doesn't particularly matter how long it is. And then we will make a vertical line as well. This vertical line, it should coincide, or this should be coincident with that center point. And it looks like we have another coincident relationship here that shouldn't exist. We're also going to select the midpoint of this line here and make that coincident too. Cool. And then remember, we're going to this center point of the wheel that we use to define this plane. We always want to make sure that our references are all consistent. So going back to this view, here we'll set our caster angle. Cool. And we set that at 6 degrees at static conditions, which is fairly reasonable. And then from here, last couple things we need to do are to, actually I'm going to make this bottom point pierce where the tire is going through. Cool. And we will make 2 lines that will define our instance center. And I want to double check to make sure that that coincidence is where I want it to be. Yes. Okay. I'm going to bring the ground plane back up just for reference so that I can dimension angles off of it. And then, like I said before, from here, all I'm going to do is I'm going to define this angle, which is phi in the front. It's 1.4 degrees. And then I'm going to set some arbitrary, or I guess not super arbitrary, but I'm going to pick a reasonable value for the side view swing arm length. In this case, it was 4 meters, which is a little over 2.5 times the wheelbase. And this, again, is kind of based on some reading I did. You can play with this a little bit and research a little bit more in terms of where you actually want this instance center to be. There's some literature out there on it. But again, we're defining this based on what we want. This phi is based on our anti-lift properties. And then in the rear, we'll have both anti-squat and anti-lift defined, since that's our driven wheel. And then, of course, we also set up our angle here for our caster, our static caster. Cool. So pretty simple sketch. And what I'm actually going to do is I'm going to move that underneath the front wheel side view, front side view swing arm. Cool. And then I'm going to hide that guy. I'm going to start a sketch on this one. And you can rotate it around so I can tell what's going on. And we will make, again, a vertical line. This is going to pierce the tire at the bottom. But not make midpoint, make pierce. And just to be extra sure that it's vertical, I'm going to make sure that that's coincident. Cool. And then you have to make it vertical. Everything should rebuild okay. If this doesn't rebuild, it means we have a problem. Because in this case, we're technically over constraining it. We have 1 point, 2 points that are defining the line, and then we're also making sure that it's vertical. So just a little sanity check that we're building in for ourselves for later on. Cool. And now we just need a line that goes from that center point out. Then it's going to come back. I'm actually going to hide this rear wheel assembly just so I know that I can go right to that end point. There we go. Cool. And now all we got to do is dimension between those two. Again, this is phi going between the ground, and then theta is going to be the one going this way, and we're actually going to drag this out farther just so that the angle is going in the upwards direction. Cool. Theta rear. Cool. And then if for some reason we wanted to measure our side view swing arm length, we could take the rear axle center line, come out to here, and we can take a look at that driven dimension now. So about 4.8 meters, which is a little over 3 times the length of our wheelbase. So again, pretty reasonable, I feel, at least. I could be very wrong, and that's okay. But yeah, so that's kind of how we define our side view swing arm lengths. And from here, it kind of all goes downhill. Rear side view swing arm. So if you kind of see this feature tree, we've been working with 2D sketches this entire time. It's time to go to 3D sketches, and this is where things get really tricky. The things with 3D sketches, it's very, very important to be very cognizant of the relations that you're creating between all your different sketch entities and your reference geometry and just be very diligent about what relations you're creating. If you want to be extra careful, you can turn on relation view here. So within this eyeball, you can view sketch relations, and that'll show you all of them. So you can see in this case, we just have two coincidences here. We have some horizontal lines. If I swap back over here, I can pop back into this sketch. We should only have a couple of relations here, and that's all we need. Cool. So, like I said, from here it's going to get a little confusing. There's more outlined within our CVD. I'm going to switch back to that and just pull up a page number real quick. Section 17.5 is what covers front suspension design. And then towards the end of that section, so starting at around page 630 and 631 are kind of what we're going to be following here. And they're pretty confusing. Hopefully working through it is going to make a little bit of sense. But basically they're operating on a couple of principles, geometrical principles, and using that to combine the front and the side views together in order to give us our control arms themselves. So I guess we should just dive right into it. I'm going to pull up the sketch here just for reference. So this is kind of what it's going to end up looking like. See, we have some construction lines. These are going to our instant centers. We have some chassis side geometry going on. We have some arbitrary lengths that we're going to be picking out, and then some lines going back. I guess let's just dive right into it. And for this, I'm actually going to have RCVD pulled up, and I'm just going to be following through it and trying to explain things as we go. Actually, I might need to... Okay. Yes. Okay. So this is, like I said, this is where it gets confusing. We're going to jump into a 3D sketch. We're going to, I'm going to hide that. I'm going to bring up, we're going to start with the front suspension. So we're just going to bring up stuff related to that. I'm going to do front suspension front view. And we're going to pull both of those in, convert both of those. And I think that should be the only things we need from that. So we just have those two lines. Again, that's our front view geometry. We're going to extend these. I'm drawing on the wrong plane. So I'm going to also make sure that I can see at least YouTube chat. Okay, so we're drawing, I don't know if you guys have worked within 3D sketches before, but right by your cursor, it shows you which plane it's like by default placing your lines on. So right now it's XY plane, YZ plane, ZX plane. I'm cycling through these with the tab key, and I'm creating some construction lines. I just converted the front view control arm lines, and I want to draw on the YZ plane by default. You can see it popped up with a collinear, which is exactly what I want. In this case, I don't want it to be along the axis. If I hover over that, it'll bring up my references, so I can do that. I also want to bring in front wheel side view plane. So I'm going to make this point onto this plane here, and make this on that plane as well. And like I said here, we're just extending those lines out, so that we can interface the front and the side view geometry as well. So from here, what we're going to do is we're going to draw a construction line or two construction lines from this instant center that we created. And again, I should probably make sure that I'm drawing on the right reference plane first. So we want to be on ZX here. And I'm going to do another one down here. Both of these are going to intersect those points. Cool. And what we're going to do is we're just going to make these arbitrarily long in front. We can kind of look at these lines from, yeah, here we go. So this is that reference line we created. What I did in this case was I just made a collinear line here. You can also just make that line coincident, either way. We're just extending this out further in front just so we can connect this line going back, which is going to be kind of weird, but we'll see it all come together here shortly. And yeah, let me just make sure again, got chat up so I can see if there's any questions. I don't know if any of you guys are following along or anything, but we'll define the dimension between front plane and this as 50 millimeters, and same thing with this. And I'll do front plane and that. Okay. So now what we're doing is we are creating a line that goes, let's start on the XY plane. Okay. From here, creating a line that's going to be coincident with that. Cool. So that defines where that's going, and then same thing here. Make that coincident. Cool. These are going to go back pretty far, and then these are effectively, you can kind of see it's starting to make like this triangle shape. This isn't exactly what our control arm is going to be, but that triangle is going to define what our control arm plane is. Let me just double check one quick thing. Just want to make sure that the camber angle, or sorry, caster angle doesn't play a role yet. No, it doesn't. It goes with the left side control arm construction. So yeah, right now we're just creating we just created this line here. That's going to go back here and interface with where our chassis is. So we're basically creating an axis that we can mount our control arm points anywhere along that axis that we want. Actually, I'm going to make both of these constructing geometry as well. But let's see, what I need to do now is actually do this. So we're going to draw on the ZX plane. We're going to make a line that is along the Z axis and along the X axis. And then we're going to merge these 2 points together. So what that did is it made sure that this was on the same it's aligned along the X axis. Or I guess it's kind of flat. I don't know how to really explain that. Basically, what we did here is we made it so that the rear point of this axis, or this axis effectively, will lie on a plane that we said, remember when we defined this front view swing arm, we said, hey, control arm points can't lie anywhere within 600 millimeters just because we got driver legs there. So we're making sure that this axis is on a plane that's 600 millimeters, or I guess 300 millimeters from the center line. So 600 millimeters between these two axes. Hopefully that makes sense. But yeah, again, we'll create our chassis side axis right now. And we'll make it coincident to that point. And then we'll make it coincident to this point as well. All right, so there's our axis. And again, this is kind of where anywhere along this line we can place 2 points, and that's where the inboard control arm mounting points are. And we'll combine this with the chassis side view later to actually make all of that work. In this case, what I did is I just set some arbitrary lengths, again, just to fully define the sketch. You don't have to do it, but it just helps to kind of make sure that, hey, I know everything's fully defined. Yeah, so you can set some arbitrary lengths if you want to. I guess I might as well do that here. Oh, there we go. All right. So smart dimension from here. So it wants me to do a diameter, or we'll just do 600 there and 300 going the other way. And this is all arbitrary just to create a fully defined sketch, so we're all happy. And then same thing here. You just have to make a line that's along Z, then along X, and merge these 2 points together. Cool. And you can see just how tiny that little discrepancy is along the Z-axis between these 2 points. But you need to make sure that it is there. So we'll make that coincident there. And we'll also make it coincident up here. All right, and there we go. We've now created our front chassis side axes. I'm going to go ahead and create the rear ones as well within the same sketch. That's what I did before. Or actually, you know what? I might as well do it in a separate one. Looking at this sketch here, it does get a little confusing. So we'll just exit out of the sketch here. Say front chassis side axes. Cool. And okay, so we'll hide that plane as well. And what else are we showing here? So we're showing that new 3D sketch we just created. So now we need rear wheel side view plane, rear side view swing arm, and rear suspension. I'm going to show all of those and jump into a new 3D sketch. I thought I showed the plane too. Okay, so from this front view sketch, we just need the 2 control arm lines there. So we can convert that geometry there and hide the sketch to clean things up. Where's this front view hide? Okay, and then we just need to extend those 2 lines out, making sure we're on YZ plane to start. Hovering over this brings up the collinear lines, so we can automatically add those constraints in. It's kind of hard to see, but there's some faint yellow lines, dashed lines that pop out after you hover over another line segment, and then you can follow those. In that case, it ended up defaulting back to the y-axis, and that's collinear. Okay, cool. Add our on-plane constraints. Same thing there. And then we draw some lines going from these points past that. And I should actually, again, make sure that I'm drawing on the right plane, because you can see that's where that's going. Looked like it was going where I wanted to, but it's actually along the YZ to start. So again, we'll start ZX there and there. Coincident. Those 2 coincident again. And we actually don't need this side view swing arm sketch anymore. And we'll dimension, again, arbitrary length from here. Anything more than 50 millimeters tends to kind of, you can kind of ballpark this at whatever you want. And if you start to read through RCVD, there's basically the geometric proof is that two lines make a plane and two planes intersecting make a line. And so what we're doing here is we're creating planes between two lines here, and then from that plane we're kind of figuring out where it intersects in other places. So like this 50 millimeters, it could be 20, it doesn't really matter, it just exists for the sake of it being a line, and that this line could theoretically be infinite length as well. So again, just keep that in mind. We're just creating, we could do this all with planes if we wanted to too. So we'll start on XY here. Cool. And then we'll make those two coincident. And then one of the other things I want to point out is as you're starting to make these lines, it doesn't actually make it like I just made a line on the XY plane or the XY planar direction, but it doesn't actually constrain it to that. The only time it constrains it is if you draw a line along an axis. So like I'm drawing a line along Y. You can see it has that along Y constraint, but it doesn't do that for the plane. It's just to kind of help you create geometry that at least kind of represents what you're actually going for. And then same thing here is what we're going to do is we're going to create line along Z, line along X. Same thing down here. One more. Cool. Merge our points together. Cool. So in this case, you can see just how far out those points are. I'm just going to bring this in to like 30 millimeters just to make it easier to look at, maybe 20. Cool. And now we have, or I guess we can create I'm also going to hide this plane. So I realized, okay, I'm drawing on ZX. Make it coincident up there, coincident over here. Cool. All right, so there's that. Again, we can define these if we really want to be thorough, making sure all of our sketches are fully defined. And then I do like to make these construction geometry. Basically, you'll start to see as we start creating more and more 3D sketches, we'll want to have, we'll want to keep track of what we just worked on and what's important versus what's referencing previous sketches. So if you remember in our front suspension or like our front views here, the only things that were that we left behind were our actual control arms. Everything else was construction geometry. So this tells me, hey, in the future, you're going to need to use these control arms for some, or these lines for something. So, that's why they're non-construction geometry. Same thing here. We don't care about any of these long lines, any of this other construction stuff here. All we care about is these two lines here, and that's it. So we can exit out of that. We can rename this to rear chassis side axes, and we're pretty much almost there. We got two more 3D sketches to make, and then we are done with our control arms themselves. And seeing as how we've spent basically 2 hours on this, I think I'm going to do a separate workshop talking about how to set up the parametric analysis and also how to do bell crank geometry there. So I'll try to do that within a couple of days here, but I didn't realize this was going to take quite so long. So we can pop out of this sketch now. This is our old one. Actually, we only have really one main 3D sketch to do, and that's our control arms. And you can see they're pretty much no dimensions here. The only dimension is for a chassis side reference here. So, we're pretty much set here in the home stretch. So, yeah, all we got to do is bring in our static camber angle here. Then we pick up our points. These are our front views again, and then we create our full control arm geometry, and that's going to be pretty straightforward. So, and then same thing in the rear. We just bring in a couple of points, and that's it. All right. So let's create a esky. There we go. Create a 3D sketch. We're going to start with the front view, and here's where we're actually going to need our chassis side view as well. We'll have our front chassis side axes too, and we'll need our front side view swing arm show. And yeah, so if you remember, these two we converted from our front view sketch. So actually, before I even go on that, always want to make sure, even though in this front chassis side view or front chassis side axis sketch, I had that same line, I'm always going to reference back to the same sketch instead of trying to create create even more of a reference tree, I guess, if that makes sense. I don't want this sketch to be referencing this sketch, which is then referencing this sketch, if I can just go directly to that main original sketch. So again, I'm going to convert these two. And then I'm going to hide that and make a construction geometry as well. And then let me just go back to this guy here just so I can look and see. Yep, so we're going to go parallel to what? Yes, okay. Yeah, okay. So we'll bring in our chassis side axes, and we'll go ahead and convert them also, just so we don't have to have all this extra sketch geometry in there. All right, and now we get to place our control arms. So there's our first control arm. And what we're going to do is we're going to try and figure out where this outer point here needs to go. So we'll do that. And this is going to be parallel with this axis here. So we basically want this to, again, from the front view, look identical, but also to be, or from the front view to not move left to right, but also to be in plane with the control arm. So this is going to be parallel. There we go. And you can see this can kind of move forward backwards. But then if we look from the front view, hopefully, we can see that this construction line here kind of defines where that's going to be width-wise. So then to figure out where this needs to be forward backward, that's where our caster angle comes in. So what we're going to do, we're going to bring that in there. And we're going to make this parallel with that. Cool. So now we have this outer point fixed, so that can't move. Now we have to figure out where our inboard points are, and that's where this chassis side constraint sketch comes in. Basically, we make a couple of lines along the y-axis. A couple stubby lines there. Then we merge these 2 points. And same thing here. Merge those 2 points. There we go. We've successfully created our first control arm. An hour and 55 minutes in. All right, so same thing on the bottom. A couple of lines on the XY plane. I'm going to make 2 construction lines. One of these is going to be coincident with this. And then the other one, geez, is going to be, actually, wait, I guess I should have done this the other way. There we go. That's coincident there. These two are parallel, or not collinear, parallel. And then that's coincident with that, and parallel with this one. So another way to think of this is you can think of this chassis side line and this front view line, those two combining to make a plane. That's our control arm plane. And then that's why we're making things parallel to them. And then, yeah, like I said before, since the chassis constraints were done from side view, anything along the y-axis will be, kind of, it'll basically be a projection of that. So merge those points, and we have our front suspension done, 100%. Cool. Or at least our static control arms. Same thing we can do with the rear chassis side axes. Let's show those. Let's convert those 2 points. Put those two there. Cool. I'm going to hide that. We're also going to show our rear suspension front view. We get those two lines coming out of that. Cool. And in this case, because we don't have any caster angle or anything like that to worry about, we can just use these lines directly, pretty much. If we wanted to induce a caster angle in the rear, we could, but pretty much for simplicity's sake, we'll just do that for one of our control arms. And we'll do this for our other control arm. And then I should go through real quick and make those construction. All right, a couple more lines going in the y-axis. And make sure we're matching up the right points. Merge. Merge. And merge. All right, so we have our both sets of control arms, and remember what we did before. We went through and we actually changed our rear outer track width. So we're going to make sure that we change that back to 60 inches, and this is the moment of truth where everything rebuilds perfectly, and yeah, no breaks. So again, keep things in mind. Make sure that you're constraining the things that need to be constrained. So I'm going to call these left set of control arms. And one of the things that I did in the other, or in the original model, was I just went through, picked out these 4 lines here, converted them, hid that, select all, mirror all those about the side plane. All right, exit sketch, hide what we don't need, and there are our control arms. So that's pretty much what I'm going to call it for today. I'm going to call this both sets of control arms. And we'll do that. We'll add them to a new folder. We'll call this control arm creation. And there we are. So like I said, I'm going to do a separate workshop talking about how to set up, let me pop out of this here real quick, how to set up bell crank design. And ultimately our end goal is going to be this really complicated or tough to get right parametric analysis sketch. This was the bane of my existence for a while. There's a reason it's a revision 2 within this exact file too, which has gone through several revisions before even being uploaded into PDM. We'll also briefly touch on steering, and then I won't go over weldments and all that kind of stuff, but yeah, so we'll talk about steering, we'll talk about bell cranks, and how to make it all parametric in a workshop coming soon TM. It'll hopefully be within the next couple of days here. So, yeah, I guess that kind of marks it for today. I left information about me in the description as well if you need to get a hold of me if you have questions about this video or anything like that. Yeah, I guess that's pretty much it for today. I'm going to save this as well and be a good friend and check it in too in case somebody wants to go poke around in this. Cool. All right. So thank you everybody for tuning in. And yeah, like I said, I'll have a workshop in a couple of days doing the rest of the file creation, going through bell cranks, parametric analysis, steering, and that should be everything. So yeah, thanks for watching. Let me know if you have questions. Leave them in the comments. Contact me directly if you'd like. Yeah, thanks for tuning in.